Okay, let me continue now. Let me use the black. So what have we discussed so far? We have discussed Cartesian tensors and non-Cartesian tensors. Okay, and while discussing Cartesian tensors, we studied transformations of Cartesian coordinates from the unprime frame to the prime frame. And for such a transformation, my x prime, y prime, z prime, they are actually related by my x prime, y prime, z prime, they are related by this equation. So let me write it like this. X1 prime is equal to A11 x1 plus A12 x2 plus A13 x3. Similarly, x2 prime is equal to A21 x1 plus A22 x2 plus A23 x3. And similarly, x3 prime is equal to A31 x1 plus A32 x2 plus A33 x3. So this is the relation between Cartesian coordinates. This is x, this is y, this is z, and then I have another set of coordinates. Let me draw it with a red line. This is x prime, this is y prime, and this is z prime. So from the unprime frame, we we have rotated to the prime frame, and then we take any point P, and the coordinates of this point P in the unprime frame are x, y, z, and the coordinates of the point P in the prime frame are x prime, y prime, z prime. I'm missing prime here. Okay, here should be z prime. Here should be z prime. Okay. Okay, this is fine. So here, let me use a spotlight. Here, x1 is actually x, x2 is y, x3 is z. So this is x prime, y prime, z prime. This is x, this is y, this is z. Okay, and we saw that for Cartesian tensors, we have this relation. Xi prime equal to a ij xj. This is for Cartesian tensors. Okay, then we had another relation for non-Cartesian tensors. So while discussing non-Cartesian tensors, we said that we generalize the idea of Cartesian coordinates to include any arbitrary coordinate system. Okay, any arbitrary coordinate system, and this coordinate system, it can transform to any other coordinate system. We are not restricting ourselves to Cartesian coordinates. Okay, so under such arbitrary coordinate transformations, we have relations like this. Let me write down the relations for arbitrary coordinate transformations. It would be dx1 prime equal to dou x1 prime by dou x1 dx1 plus dou x1 prime by dou x2 dx2 plus dou x1 prime by dou x3 dx3. Similarly, dx2 prime is equal to dou x2 prime by dou x1 dx1 plus dou x2 prime by dou x2 dx2 plus dou x2 prime by dou x3 dx3. Similarly, we have dx3 prime equal to dou x3 prime by dou x1 dx1 plus dou x2 prime by dx2, sorry, dou x2 dx2 plus, sorry, this would be 3. Dou x3 prime by dou x3 dx3. So this is the relation between the coordinate differentials. Okay, this is the relation between the coordinate differentials for arbitrary coordinates. Arbitrary coordinates x1 prime, x2 prime, x3 prime. So we are transforming from x1, x2, x3 to x1 prime, x2 prime, x3 prime. Here, there is no restrictions on x1, x2, x3, and x1 prime, x2 prime, x3 prime. By restriction, I mean x1, x2, and x3 need not be the excess of the Cartesian coordinates. I repeat, so the x1, x2, x3 है Cartesian coordinates with variable. Any other curvilinear coordinates will be variable. Similarly, x1 prime, x2 prime, x3 prime, these are curvilinear coordinates. Okay. And here in index notation, this set of equations, it can be written like this. This is dxi prime. Saya give tu dxi prime equal to dou xi prime divided by dou xj dxj. For the time being, let me use the subscript notation. I'll change it back to superscript notation later on. Okay. So this is how the differentials are, coordinate differentials are related for arbitrary coordinate transformations. And this is how the coordinates are related for transformation from one Cartesian coordinate system to another Cartesian coordinate system through a rotation. Okay, so far so good. So let me come back to this. So if I compare this and this, we can easily see that this Cartesian, this tensor is a special case of this general tensor. Okay, because dou xi prime by dou xj, dou xi prime by dou xj, from here dou xi, from here dou xi prime by dou xj, if I actually perform this partial differentiation, I'll get an equation of this form. Okay. Okay. So what is a Cartesian vector? Cartesian vector, have it kind of a Cartesian vector is a quantity whose components transform like this. Equation J. So minor transform to. Say for example, let us consider a Cartesian vector V. So let us consider a Cartesian vector V. We have a Cartesian vector. Then the components of this Cartesian vectors, it should transform like this. This Vi prime should be equal to Aij Vj. So what is Vj? Vj is so let me use the spotlight. So what is Vj? Vj is actually the component of the vector in the unprimed coordinate system. So let me draw the vector here. Suppose this is some vector. This is some vector V. Okay. So what is Vj? Vj is the component of this vector V in the unprimed coordinate system. That is x coordinate, y coordinate, z coordinate. So V1 is the component of the vector V along the x-axis. v2 is the component of the vector v along the y-axis, and v3 is the component of the vector along the z-axis. Okay. Now, when the coordinate is rotated from the xyz system to the x prime y prime z prime system, the components of v will also change. Okay, and the new components of v in the new rotated coordinates, this is actually vi prime. It's given by vi prime. So v1 prime is the component of the vector v, of the same vector v along the x prime axis. And v2 prime is the component of the same vector v along the y prime axis. And v3 prime is the component of the vector v along the z prime axis. So the new components of v in the prime axis, in the prime coordinate system, and the old components of v in the unprime coordinate system, they are related by this equation. By this equation, where aij's are given by this aij's. That is the direction cosines of the angle between xi prime and xj. Okay. So any quantity whose components transform according to this rule is called a vector. And we can also say that vector is a tensor of rank 1. This is fine. So this is how we define a Cartesian vector. Okay, I repeat, any quantity whose components transform according to this rule is called a Cartesian vector. Now let us come back to general vectors. How about general vectors? So this is all about Cartesian vectors. So how about general vector? A general vector, here you can see that a general vector is a vector whose components transform according to this rule. Whose components transform according to this rule under a change of coordinate from the unprime system to the prime system. Here, in this particular case, the coordinate system are curvilinear coordinate systems. They need not be Cartesian coordinate system. Cartesian coordinate system, they are any curvilinear coordinate systems. So any quantity whose components transform according to this rule is called a general vector. And you can see that this Cartesian vector is a special case of general vector. I repeat, this Cartesian vector is a special case of general vector when we take this xj and xi as Cartesian coordinates, because this dou xi prime by dou xj is actually aij from this equation. Okay, so this particular relation is a special case of this relation. Okay, this is fine. Now let us look at another example. So let me add a new page. Another example. Let me use here. Let me change my sheet. Another example here. Let us consider the partial derivative of a function. I repeat, if we consider the partial derivative of a function u is a function which depends upon the coordinates xi. Okay, so u is a function which depends upon the coordinates x1, x2, x3. In short, I have written xi. Okay, so let us calculate the partial derivatives of u. Dou u by dou xi. Okay, this dou u by dou xi are the components of the partial derivative of u. In short, dou u by dou xi are actually the components of the gradient of u with respect to the xi's of the coordinate system. And here xi's are actually the coordinates of a curvilinear coordinate system. Okay. Now, if we change the coordinate system from the unprimed system frame to the prime frame, how will the components of the gradient change? That is, what is the relation between dou ui by dou xi prime and this? What is the relation between these two? This is what we want to find out. Okay. I repeat, this is the component of the gradient in the unprimed frame. This is the components of the gradient in the prime frame. And we are transforming the coordinate system from one curvilinear system to another curvilinear system. This is a general coordinate transformation. Okay. This is not restricted to Cartesian coordinates. This is a general coordinate transformation from one curvilinear coordinate system to another curvilinear coordinate system. So from we can use the property of partial derivatives to write it like this. So this is dou u by dou xj by dou xi prime. Okay, here we are using the property of partial derivatives, and here what is the repeated index? The repeated index here is j. That means it has been summed over. What is the meaning? Summed over means it is actually this. This is dou u by dou x1 by dou xi prime plus dou u by dou x2 by dou xi prime plus dou u by dou x3 by dou xi prime. Here j is summed over means we actually have three terms like this. Okay, now I can rearrange these two and write it like this. This is dou xj by dou xi prime, and I can write it here. So dou u by dou xj, and this is equal to here dou u by dou xi prime. So this is how the components of the gradient transform when we transform our coordinates from one system to another. And why are we discussing this? We are discussing this because if we look closely, let me rewrite it here. If we look closely and compare it with how the differentials of coordinates transformed under a coordinate transformation, the relation we had obtained was something like this. dxi prime, this is equal to dou xi prime by dou xj dxj. This was what we obtained in our earlier page. Let me show it in our earlier page. It is this. Okay, this is here. It is here. dxi prime is equal to dou xi prime by dou xj dxj. So I have simply rewritten it here on page number 2. So I have rewritten it here. So this is how the coordinate differentials transform under an arbitrary coordinate transformation. And this is how the components of the gradient transform under similar arbitrary coordinate transformations. If you look here, this is dou xj by dou xi prime. But here we have dou xi prime by dou xj. Okay, so these two, they are reciprocal of each other. Yarba? Okay. So that means the manner in which the components of the gradient transform is not the same as the manner in which the differentials of the coordinate transform. Right? So we have two different transformation rules. One for the components of the gradient and the other for the coordinate differentials. And it is an interesting exercise to show that for Cartesian tensors, these two give exactly the same answer. I repeat, for Cartesian tensors, these two give exactly the same answer, that is Aij. For Cartesian tensors, this is the same Aij. So we have no problem with Cartesian tensors. But when we consider general tensors, these two are different. Dou xj by dou xi prime, dou xi prime by dou xj. Okay, so in general, what do we have now? In general, we have two possible definitions of a vector. Okay, so we have two different possible definitions of a vector when we consider general coordinate transformations. For Cartesian vectors, these two are the same, but for general vectors, these two are not the same. Okay, so from this comes the definition of covariant vector and contravariant vector. I'll discuss covariant vector and contravariant vectors in our next class. So let me pause the recording here.